Welcome friends. In this session, we will derive formulas for the derivative of trigonometric functions sin x, cos of x, tan x, cot x, sec x and cosec x. We assume in this session that the variable x in the trigonometric functions is measured in radians. To find the derivative of the trigonometric functions, we use the definition of derivative of a function at a point and various rules of limit of functions discussed in the earlier sessions. We also see that we do not always depend on the definition of derivative to find the derivative of trigonometric functions. Sometimes using non-derivative formula of trigonometric functions and rules of differentiation such as quotient rule, we can derive formula for derivative of other trigonometric functions. Also, in these sessions, we explore the relationship between the derivative of a function and derivative of its inverse. For functions whose derivative we already know, we can use this relationship to find the derivative of inverses without having to use the limit of definition of the derivative. In particular, we will apply the formula for derivatives of inverse functions to trigonometric functions. Let us begin by finding the derivative of f of x equal to sin x. We use the definition of derivative of a function f dash x equal to limit h tends to 0 of f of x plus h minus f of x whole divided by h, and with f of x equal to sin x, we obtain d by dx of sin of x equal to f dash x equal to limit h tends to 0 of sin of x plus h minus sin x whole divided by h. Now, using the trigonometric identity sin of a plus b equal to sin a cos b plus cos a sin b, the above gives d by dx of sin of x equals limit h tends to 0 of sin x into cos h plus cos x into sin h minus sin x whole divided by h. By bringing common factors together, we obtain d by dx of sin of x equal to limit h tends to 0 of sin x into cos h minus 1 whole divided by h plus cos of x into sin h by h. A rearrangement gives d by dx of sin of x equal to limit h tends to 0 of cos of x into sin h by h minus sin x into 1 minus cos h whole divided by h. Now, applying the difference rule and product rule of limit of functions, we obtain d by dx of sin of x equal to limit h tends to 0 of cos x into limit h tends to 0 of sin h by h minus limit h tends to 0 of sin x into limit h tends to 0 of 1 minus cos h by h. As sin x and cos x do not involve h, the value of limit h tends to 0 of cos x equal to cos x and limit h tends to 0 of sin x equal to sin x, and hence the above gives d by dx of sin of x equal to cos of x into limit h tends to 0 of sin h by h minus sin x into limit h tends to 0 of 1 minus cos h by h. Using the limits, limit h tends to 0 of sin h by h equal to 1 and limit h tends to 0 of 1 minus cos h by h equal to 0, the above gives d by dx of sin of x equal to cos of x into 1 minus sin of x into 0, that is d by dx of sin x equal to cos x. Similarly, the following identity will be obtained: d by dx of cos of x equal to minus sin x. The chain rule of differentiation of the function of one variable states that if w equal to g of I and y equal to h of x are differentiable functions of y and x respectively, then their composition w equal to g of h of x is a differentiable composite function of x, and dw by dx equal to dw by dy into dy by dx. W equal to sin y, hence with we have d by dx of sin y equal to cos y into dy by dx. Similarly, d by dx of cos y equal to minus of sin y into dy by dx. In evaluating the derivatives of the remaining 4 basic trigonometric functions, of course, we can use the definition of derivative of a function, but it is easier to use the formula for derivative of sin x and cos x and apply quotient rule as we explain now. We have the relations tan x equal to sin x by cos x, cot x equal to cos x by sin x, sec x equal to 1 by cos x, cosec x equal to 1 by sin x. For finding the derivative of tan x, we proceed like this: d by dx of tan x equal to d by dx of sin x by cos x. Now, applying the quotient rule of differentiation, we obtain d by dx of tan of x equal to cos of x into d by dx of sin x minus sin of x into d by dx of cos of x all divided by cos square x. Using quotient rule of differentiation, cos of x into cos of x minus sin of x into minus sin x all divided by cos square x, that equals cos square x plus sin square x all divided by cos square x, that equals 1 by cos square x, that is d by dx of tan x is equal to sec square x. Proceeding similarly, using the relation cot x equal to cos x by sin x, it can be seen that d by dx of cot of x equal to minus of cosec square x. An application of chain rule gives d by dx of tan y equal to sec square y into dy by dx, and d by dx of cot y equal to minus of cosec square y into dy by dx. Now, to evaluate the derivative of sec x, we use the relation sec x equal to 1 by cos x and apply the quotient rule. Using quotient rule of differentiation, d by dx of sec x equal to cos of x into d by dx of 1 minus 1 into d by dx of cos of x all divided by cos square x, which equals cos of x into 0 plus sin x all divided by cos square x, same as sin x by cos square x, that equals 1 by cos x into sin x by cos x, that is d by dx of sec x equal to sec x into tan x. Proceeding similarly, using the fact cosec x equal to 1 by sin x, we obtain d by dx of cosec x equal to minus of cosec x into cot x. An application of chain rule gives d by dx of sec y equal to sec y into tan y into dy by dx, and d by dx of cosec y equal to minus of cosec y into cot y into dy by dx. With the above basic derivative formulas, we can find the derivative of the product of functions of which one function is a trigonometric one. As an example, let us find the derivative of f of x equal to x square into tan x. Using the product rule of differentiation, d by dx of x square tan x equal to f dash x equal to x square into d by dx of tan x plus tan x into d by dx of x square equals x square into sec square x plus 2x tan x. As in another example, we find dy by dx if y equal to sin x by 1 plus cos x. Using quotient rule, dy by dx equal to 1 plus cos x into d by dx of sin x minus sin x into d by dx of 1 plus cos x all divided by 1 plus cos x whole square, same as 1 plus cos x into cos x minus sin x into minus sin x all divided by 1 plus cos x whole square. equals cos x into cos square x plus sin square x all divided by 1 plus cos x whole square equals 1 plus cos x all divided by 1 plus cos x whole square equal to 1 by 1 plus cos x. Now, we explain how to find higher order derivative of trigonometric functions. As an example, let us find the value of the second derivative of y of x equal to sec x at x equal to pi by 4. Already we know that d by dx of sec x equal to sec x into tan x, that is y dash x equal to sec x into tan x. Now, the second derivative of y of x is obtained by differentiating y dash x with respect to x. By applying the product rule of differentiation, the above gives y2 dash of x equal to d by dx of y dash of x equal to sec x into d by dx of tan x plus tan x into d by dx of sec x. That is y2 dash of x equal to sec x into sec square x plus tan x into sec x into tan x, same as sec of x plus sec x into tan square x. Now, the value of the second derivative of y of x equal to sec x at x equal to pi by 4 is obtained by putting x equal to pi by 4 in y2 dash of x, which gives y2 dash of pi by 4, that equals sec cube of pi by 4 plus sec of pi by 4 into tan square of pi by 4, that is same as root 2 all cube plus root 2 into 1 square, same as 3 into root 2. As another example, the derivative of y equal to cosec x minus 4 into root x plus 7 with respect to x is dy by dx equal to minus of cosec x into cot x minus 4 into 1 by 2 into x to the power 1 by 2 minus 1 plus 0, same as minus of cosec x into cot x minus 2 by root x. We will now show that if y equal to sec x plus tan x into sec x minus tan x, then dy by dx equal to 0. Given equation can be written as y equal to sec square x minus tan square x. Thus, dy by dx equal to d by dx of sec square x minus d by dx of tan square x. By applying chain rule, the above gives dy by dx equal to 2 sec x into d by dx of sec x minus 2 tan x into d by dx of tan x, that equals 2 times sec x into tan x minus 2 tan x into sec square x, the difference is equal to 0. As another example, let us find the derivative of y equal to cot x divided by 1 plus cot x with respect to x. By applying the quotient rule for differentiation, dy by dx equal to 1 plus cot x into d by dx of cot x minus cot x into d by dx of 1 plus cot x all divided by 1 plus cot x whole square, same as 1 plus cot x into minus of cosec square x minus cot x into minus of cosec square x all divided by 1 plus cot x whole square equals minus of cosec square x all divided by 1 plus cot x whole square. Now, we are going to discuss the derivative of inverse trigonometric functions. For this, we first discuss the method of obtaining derivative of an inverse of a given function from the derivative of the given function. Suppose that f is a one-to-one differentiable function such that at the point ordered pair a f a, the derivative f dash of a not equal to 0, then the equation of the tangent at the point ordered pair a f a is y minus f a equal to f dash a into x minus a. Since the graph of y equal to f dash x is the reflection of the graph of y equal to f of x about the line y equal to x, comma the tangent line to the y equal to f inverse of x at the point ordered by f a is the reflection about the line y equal to x of the tangent line to the y equal to f of x at the point ordered pair a f a. That is, the tangent line to y equal to f inverse of x at the point ordered pair f a is the graph of the function which is the inverse of the function whose graph is the tangent line to y equal to f of x at the point ordered pair a f a. Hence, the equation of the tangent line to y equal to f inverse of x at the point ordered pair f a can be obtained from that of the tangent line to the graph of f by interchanging x and y, which gives x minus f a equal to f dash a into y minus a, or y minus a equals 1 by f dash a into x minus f a. We notice that slope of the tangent line to y equal to f inverse of x at the point ordered pair f a is 1 by f dash a. We have to impose some mathematical conditions on f to be sure that this conclusion holds. We state that the conditions and the conclusions in the following result. Theorem: derivative rule for inverses. If f is 1 to 1 function that is differentiable at every point on the interval I, and dy by dx is never 0 on I, then f inverse is differentiable at every point on the interval f of I. The value of d by dx of f inverse at any particular point f a is the reciprocal of the value of df by dx at a. That is, d by dx of f inverse at x equal to f of a is same as 1 by df by dx at x equal to a. In short, f inverse dash equal to 1 by f dash. Next, the derivative of y equal to sin inverse of u. From the discussion at the beginning of this session, we know that the function x equal to sin y is differentiable for every real value y, with its derivative is given by x equal to cos y. By looking at the figure, we can see that x equal to cos y is strictly greater than 0 in the open interval minus pi by 2 less than y less than pi by 2. Hence, x equal to sin y is differentiable at every point on the open interval open minus pi by 2 pi by 2, and its derivative never 0 in that interval. Hence, by the derivative rule for inverses, the inverse function y equal to sin inverse of x, that is y equal to arc sin x, is differentiable throughout the interval sin of minus pi by 2 less than x less than sin of pi by 2, that is the interval minus 1 less than x less than 1. The graph of y equal to sin inverse of x with the minus 1 less than x less than or equal to 1 is drawn by taking the reflection of the graph of y equal to sin x in minus 1 less than or equal to x less than or equal to 1 about the line y equal to x. When x equal to minus 1, cos of sin inverse of x equal to cos of sin inverse of minus 1 equal to cos of minus pi by 2 equal to 0, and when x equal to 1, cos of sin inverse of x equal to cos of sin inverse of 1 equal to cos of pi by 2 equal to 0. Hence, we cannot expect y equal to sin inverse of x to be differentiable at x equal to 1, or at x equal to minus 1. Hence, when minus 1 less than x less than 1, the derivative of the inverse sine function is given by d by dx of sine inverse of x at x equal to sine y equals 1 by d by dx of sine x at x equal to y equal to 1 by cos y, that equals 1 by square root of 1 minus sin square y, that equals 1 by square root of 1 minus x square. As an alternative method, we are going to obtain the derivative of the inverse sine function y equal to sine inverse of x with minus 1 less than x less than 1 by writing it as sin y equal to x with minus 1 less than x less than 1 and differentiating implicitly with respect to x as follows. Differentiating with respect to x, sin y equal to x gives by an application of chain rule that cos of phi into dy by dx equal to 1 with a minus 1 less than x less than 1. As cos y not equal to 0, when minus pi by 2 less than y less than pi by 2, comma dividing the above equations by cos y, we obtain dy by dx equal to 1 by cos pi in the range minus 1 less than x less than 1. Now, referring the right angle triangle in figure, we obtain cos y equal to square root of 1 minus x square by 1, that is same as square root of 1 minus x square in minus 1 less than x less than 1. Thus, dy by dx equal to 1 by square root of 1 minus x square with minus 1 less than x less than 1. Thus, d by dx of sin inverse of x equals 1 by square root of 1 minus x square with mod x less than 1. Similarly, it can be seen that d by dx of cos inverse of x equal to minus of 1 by square root of 1 minus x square with mod x less than 1. If u is a differentiable function of x with mod u less than 1, we apply the chain rule dy by dx equal to dy by du into du by dx to the function y equal to sin inverse of u. We obtain the following generalized version: d by dx of sin inverse of u equals 1 by square root of 1 minus u square into du by dx with mod u less than 1. Similarly, d by dx of cos inverse of u equals minus of 1 by square root of 1 minus u square into du by dx with mod u less than 1. The method used to derive the above formulae can be used to obtain generalized derivative formulae for the remaining inverse trigonometric functions. The following is a complete list of these formulae. Each of the formulae is valid on the natural domain of the functions that present in the right side along with du by dx. Derivative of the inverse trigonometric functions: d by dx of sin inverse of u equal to 1 by square root of 1 minus u square into du by dx with mod u less than 1, d by dx of cos inverse of u equal to minus of 1 by square root of 1 minus u square into du by dx with mod u less than 1, d by dx of tan inverse of u equal to 1 by 1 plus u square into du by dx, d by dx of cot inverse of u equal to minus of 1 by 1 plus u square into du by dx, comma d by dx of sec inverse of u equals 1 by mod u into square root of u square minus 1 into du by dx with mod u greater than 1. Finally, d by dx of cosec inverse of u equals minus of 1 by 1 mod u into square root of u square minus 1 into du by dx with mod u greater than 1. As an illustration, we will prove one of the above formulae. The remaining will follow in a similar way. We derive d by dx of sec inverse of u equals 1 by mod u into square root of u square minus 1 into du by dx with mod u greater than 1. We find the derivative of y equal to sec inverse of x with mod x greater than 1 using the method of implicit differentiation as follows. We will write y equal to sec inverse of x with mod x greater than 1 to the form sec y equal to x with mod x greater than 1. Now, differentiating with respect to x, an application of chain rule gives that sec y into tan y into dy by dx equal to 1. Since mod x is greater than 1, we have y equal to sec inverse of x lies in open 0 pi by 2 union open pi by 2 pi, and hence sec y into tan y not equal to 0. Thus, the above equation gives dy by dx equals 1 by sec y into tan y. Now, we refer to the two triangles in the given figure. One in the first quadrant with sec y equal to x by 1, and another one in the second quadrant with sec y equal to x minus x by minus 1. In both quadrants, sec y equal to x. In the first quadrant, tan y equal to square root of x square minus 1 by 1 equal to square root of x square minus 1. In the second quadrant, tan y equals square root of x square minus 1 by minus 1, same as minus of square root of x square minus 1. Using the above two equations, dy by dx equals 1 by sec y into tan y gives dy by dx equal to plus or minus 1 by x into square root of x square minus 1. By looking at the graph of y equal to sec inverse of x, it can be seen that for mod x greater than 1, the slope of the graph of y equal to sec inverse of x is always positive. Hence, d by dx of sec inverse of x equals 1 by x into x square root of x square minus 1 if x is greater than 1, and minus of 1 by x into square root of x square minus 1 if x is less than minus 1. With absolute value, we can write the above equations in a single formula. D by dx of sec inverse of x equals 1 by mod x into square root of x square minus 1 if mod x is greater than 1. If u is a differentiable function of x with mod u greater than 1, we apply the chain rule to obtain d by dx of sec inverse of u equals 1 by mod u into square root of u square minus 1 into du by dx with mod u greater than 1. Using the above formula, we find the derivative of y equal to cos inverse of 1 by x with respect to x as follows. Now, y equal to cos inverse of 1 by x implies cos of y equal to 1 by x, which implies sec y equal to x. That implies dy by dx equal to 1 by mod x into square root of x square minus 1 into y equal to sec inverse of x if mod x is greater than 1. Conclusion. In this session, we have derived formula for the derivatives of trigonometric functions using any one of the two methods, using the definition of derivative of a function at a point and various rules of limit of functions. Alternately, we have found the derivative of trigonometric functions using the non-formulae for derivatives of trigonometric functions and rules of differentiation such as quotient rule. Also, in this session, we used the relation between the derivative of a function and derivative of its inverse to obtain the formula for derivative of inverse trigonometric functions. Hope the session was beneficial to you. See you next time. Until then, goodbye.